Hello everyone. In this video we are going to discuss about modeling and analysis of PEM fuel cell system using Matlab Simulink. This example shows how to model and analysis of a proton exchange membrane fuel cell stack system to set up electrical load, different type of electrical load, and how to produce by the system and how to the power consumed by the system are discussed now. Then plot the fuel cell IV curve here, and analysis the efficiency and utilization and temperature in the fuel cell system, and also hydrogen consumed by the fuel cell also we are going to discuss. Here these are the contents in this modeling and analysis of fuel cell system using Matlab Simulink. Here introduction about PEM fuel cell system and introduction about Matlab Simscape physical modeling. By using Simscape physical modeling, how to develop an PEM fuel cell system and how to model and how to analyze by using the interactive Simscape Explorer and interactive moist air properties blocks, and also interactive MEA components also we are going to discuss. Then modeling and analysis of fuel cell system using Matlab Simulink model and moist air properties block systems, and finally we are going to discuss about the simulation and result analysis by using the Simulink scopes, and also what are the products you need for this design, Matlab and Simscape physical modeling toolbox. Then this is our introduction about PEM fuel cell system. This is our model. This example shows how to model a proton exchange membrane fuel cell stack with a custom Simscape block. By using this one, here in this block diagram we are going to see this is a hydrogen source and recirculation unit, anode humidifier, the same thing in this side, oxygen source and cathode humidifier, and anode gas channels and cathode gas channel. In between where membrane electron assemblies are placed here, one heat dissipation unit also there, one cooling system, interactive cooling system. Here MEA thermal mass subsystem are involved here. Here in the same thing, the anode humidifier and cathode humidifiers are involved. Here this electric load for simulation we are going to see. Here the fuel cells, this fuel cell generates electrical power by consuming hydrogen and oxygen producing by water vapor here. Then this custom block represent the membrane electron assembly, this one MEA, this simply is called as MEA, membrane electrode assembly, and is connected to separate moisture networks here, one for anode gas flow and another one is for cathode gas flow. Here these are our Simulink model of PEM fuel cell system. Here in this electrical load we are going to give three different electrical load. First one is a drive cycle based and another one is a ramp or step based. Here by using this Simulink model we can able to plot fuel cell current versus voltage curve, and plot the power produced and consumed by the system, and plot efficiency and utilization, and plot temperature in the fuel cell, and also this coolant system, and also you can analyze hydrogen consumed by the fuel cell, and also one open models workspace also there. By using you can give this definition script also, sir, also you can see. Then the important block referenced by the Simscape component, that is a MEA block code. Then each and every block we are going to see. First one hydrogen source and recirculation unit, anode humidifier and anode gas channels. These are all with this hydrogen source and anode gas channels. Here oxygen source and cathode humidifier and cathode gas analyzer. Here your electrical load. Here one heat dissipation unit and cooling system with this anode and cathode exhaust. Finally measurement system to measure the current and voltage and power and temperature by this scope. And also interactive Simscape Result Explorer are also there in Matlab Simulink. You can also analyze the output of each and every nodes. Okay, these are hydrogen source subsystem. Here we start from this hydrogen source subsystem. Here what is the hydrogen source? In between here in this hydrogen source is a subsystem. In this subsystem this is the Simulink models is also there. In this model we are pressure reducing valve and stack pressure and fuel tank and fuel properties are going to analyze here. Here moisture from the moisture air block subsystem you can able to get the pipe and fuel tank model. Here in this system's output is we are going to analyze the fuel cell properties. Fuel properties, it is a dry air which is nitrogen and H2O and hydrogen. Here in this fuel cell valve system, here fuel cell properties, how to get from this moist air blocks. Here by using this parameter, by using this block, that is a moist air properties block, we can able to represent different gas mixtures. Okay, here the anode network consists of nitrogen, water vapor, and hydrogen representing the fuel. Here the hydrogen is stored in the fuel tank at 70. Here this is a fuel tank at 70 MPa, and a pressure reducing valve releases the hydrogen to the fuel cell stack around 0.16 MPa. Here this one, pressure reducing valve. Unconsumed nitrogen is recirculated back to the stack, and the cathode network consists of nitrogen, water vapor, and oxygen representing air from the environment. A compressor brings here this compressor brings air to the fuel cell stack at a controlled rate to ensure that the fuel is not starved of oxygen. And finally the back pressure, this one, the stack pressure unit also responsible for back pressure relief valve, maintains a pressure of around 0.16 MPa in the stack and vents the exhaust to the environment. Here itself in this block provides moisture properties to the connected moisture network, and also reusable codes also there. In this, by using this code, you can set the specific gas constant, temperature vector, and specific enthalpy vector, and conductivity vector, and valid pressure, and minimum valid pressure, maximum valid pressure. So on, you can set these parameters by using the fuel parameters block. It is obtained from moisture properties block. Yeah, then MEA block. Previously we can see the MEA block, moisture properties block. This one MEA block, that is it is responsible for designing this membrane electrode assembly block. Here this fuel cell model blocks block models a stack of membrane electrode assemblies for a proton exchange membrane fuel cell. Here this hydrogen and oxygen consumed from the connected anode and cathode flow channels respectively here. And also the higher temperature increases thermal efficiency, but reduce relative humidity, which causes high membrane resistance. Therefore in this model the fuel cell stack temperature is kept at 80 degree Celsius. The cooling system circulates coolant between cells to absorb heat and reject it to the environment by the radiator. Here the humidifiers saturate the gas with the water vapor to keep membrane hydrated and also minimum electrical resistance. Here itself you can able to set the parameters. Also by using this two source, you can also set these parameters in this Matlab script. Here this custom MEA block code. Here by using this custom MEA block code, we can model internal energy storage in a thermal network. Okay, here it is obtained from fuel cell SSC Simulink block. This block is implemented in the Simscape code fuel cell.ssc. Okay, then output of port F, this one, the output of port F of the anode and the cathode gas channels pipe blocks provide the gas mole fractions needed to the model to the fuel reactions. The removal of H2 and O2 from the anode and cathode gas flows are implemented by controlled trace gas source blocks, that is the previous blocks, MEA blocks. The production of hydrogen H2O and the transport of water vapor across the MEA is implemented by controlled moisture source block also. This heat is generated by the reaction is sent through the thermal port H and connected thermal mass block. Here the rate of temperature increases is proportional to the heat flow rate into the material and inversely proportional to the mass and specific heat of the material. Here then next one is a recirculation subsystem block. Previously we discussed with this hydrogen source. The next one is a recirculation subsystem design using feedforward controller. This by using the feedforward controller and the exhaust gas recirculation block and maximum flow and minimum flow subsystem. That is a recirculation subsystem contains this feedforward controller. And the next block is Anode Humidifier Subsystem design using proportional controller. Previous one is a feedforward controller for recirculation subsystem and a proportional controller for Anode Humidifier Subsystem. The next one is a Purge Valve Block by using to analyze the Anode Exhaust Subsystem. The next one, Cathode Exhaust Subsystem using pressure relief valve block. In this pressure relief valve block can analyze the Cathode Exhaust Subsystem design. And this one, Anode Gas Channel Subsystem. Similarly for Cathode Gas Channel Subsystem and Cathode Humidifier Subsystem design using proportional controller to analyze the relative input is relative humidity. And Oxygen Source Subsystem design with Compressor Control Block. This is an important block to get the control signals. With this input is oxygen excess ratio and stack current, and also you can see the mass to analyze the air properties by using what is the air intake and all. You can go analyze this one by using the compressor control model. You can get the mass flow rate. This is for mass flow rate block. This one MS mass flow rate block. By using this scope here in this compressor control, this is the subsystem. Under the compressor control system, we are getting this sub-circuit. In this, by using the sub-circuit, we can get the output signal like set point versus measured point mass flow rate, and also similarly by without delay and with delay. Also, you can able to analyze by using this compressor control block for measuring the mass flow rate. The next one, the design of Coolant System. Design with the pump control block. By using this pump control block, you can able to set this stack temperature and control output. Here the set point measure, the same thing, set point measured output and temperature, and control output shows the without delay and with delay. And by using the interactive measurement block in this scope system, you can analyze the peak finder, cursor measurements, signal statistics, and also bi-level measurements. And also you can see the overshoot and undershoots point there. Here by using this pump control block, you can analyze the stack temperature and control signals for designing the controller system, coolant system design. The output scopes of the coolant system design is with stack temperature and the control outputs without delay and with delay. And finally, we are going to see the current voltage curve for the fuel cell stack. With this measurement, by using the Simulink measurement scope, you can able to see the current, voltage, and power and stack temperature in the fuel cell. This plot shows the current voltage curve of a fuel cell in the stack. As the current ramps, you can see at the current ramp up and initial drop in the voltage occurs due to electrode activation loss, followed by a gradual increase in a voltage due to ohmic resistance. Near maximum current, a sharp drop in voltage occurs due to gas transport related losses. This plot also shows the power produced by the fuel cell. When the ramp scenario is selected, the power increases until a maximum power output, then it decreases due to high losses near this maximum current. The next one is by using Simscape Result Explorer, you can see the fuel cell stack power and heat performance. Okay, here how much power produced and consumed in terms of kilowatts is there. In this graph shows the net gain, electrical and air compressor power, and coolant pump power. Also you can this model shows the heat dissipated in terms of kilowatts. This plot shows the electrical power produced by the fuel cell stack as well as the power consumed by the cathode air compressor and the coolant pump to maintain stable and efficient system operation. This plot also shows the excess heat generated by the fuel cell stack, which must be removed by the coolant system. The maximum power produced by the fuel cell is 110 kilowatts. As a result, the net power produced by the system is a few percent less than the power produced by the stack. Here, what is note this model is assumes isentropic compressor are used here. Assume. And this plot curve shows the IV part. This plot shows the current versus voltage curve of a fuel cell in the stack. As the current ramps, an initial drop in voltage occurs due to the electrode activation losses, followed by a gradual decrease in voltage due to ohmic resistance. Here, this maximum current, a sharp drop in a voltage occurs due to gas transport related losses. This plot also shows the power produced by the cell, and when ramp scenario is selected, the power increases until a maximum power output, then decreases due to high losses near maximum current. Yeah, then this plot shows the thermal efficiency of the fuel cell and its reactant utilization fraction, and the theoretical maximum efficiency for a PEM fuel cell is 83%. The thermal efficiency indicates the fraction of hydrogen fuel energy that the fuel cell has converted to useful electrical work. This is a reactant utilization plot. This plot is this reactant utilization is fraction of reactants, hydrogen and oxygen flowing into the fuel cell stack that has been consumed by the fuel cell. This from plot shows thermal efficiency and reactant utilization plot. And finally, we are going to see the fuel tank pressure and energy plot. Here, this plot shows the marks of hydrogen used during operation and the corresponding decrease in the hydrogen tank pressure. The energy of consumed hydrogen fuel is converted to the electrical energy. Okay, then the temperature and coolant pump mass flow rate analysis. By using this plot, we can analyze the temperature at various locations in the system, at the stack, anode inflow, cathode inflow, coolant at the stack, and coolant at radiator. In this model, the cooling system is operated by a simple control of coolant pump flow rate. Here, the fuel flowing to the anode is warmed by the recirculated flow. Air flowing to the cathode is warmed by the compressor. Also, maintaining the optimal temperature is critical to the operation of the fuel cell, because higher temperature lower the relative humidity, which increases the membrane. So that this block is important to analyze this mass flow rate. Okay, then the second plot, this is a coolant pump mass flow rate plot, shows the temperature of the coolant after it absorbed heat from the fuel cell stack and after it has rejected heat in this radiator. Here the fuel cell stack temperature is maintained at a maximum of 80 degrees Celsius by this cooling system. Then by using this interactive Simscape Result Explorer, it is an interactive tool that lets you navigate and plot the simulation data lagging results. It contains logged simulation data for the old model. For example, these are SSC fuel cell model. Here itself, this each and every node we can see. As this root node is SSC fuel cell. It is selected in the left hand side of the left pan by default. As you may expand by using this plus button, they select nodes in the left pan, the corresponding plots appear in this right pan. By clicking this node, that represent a block display plots of all the variables in this block. Also, it contains logged simulation data for the old model. When you click a model in the left pan, a Simscape Result Explorer, the corresponding plots appear in the right pan. Okay, let us see the simulation. This is a Simulink model. These were as we explained in PPT session. This is a hydrogen source. This hydrogen source is a subsystem. Here, by using the pressure reducing valve and stack pressure, these are fuel cell properties. Here, this is a pressure reducing valve. Also, we can set the parameters. What is the use of this pressure reducing valve subsystem? Is this subsystem models a pressure reducing valve that maintains a set pressure of at this port B. The value is normally open. When the pressure is above is the set pressure, it is fully closed. Similarly, set the fuel properties, dry air and water vapor and trace gas by using this moisture properties. This block provides moisture properties to the connected moisture network here by using this pipeline. This moisture mixture is composed by dry air, water vapor and an optional trace gas, that is hydrogen. The default trace gas is carbon dioxide here. By using this reusable source code, also you can set these parameters. Here itself you can set the parameters. Here the source code, in this example the source code is available. Okay, the next block, this is stack pressure is given the 0.06. This is a fuel tank block. Here also it is obtained from this Simscape physical modeling toolbox. This block models mass and energy storage in the moisture network. The chamber contains a constant volume of moisture. The pressure and temperature evolve based on the compressibility and thermal capacity of the moisture volumes. Here you can set this main settings. Also you can set by using the source code component constant volume chamber block. This also contains from physical modeling block, Simulink physical modeling block. Here you can set the moisture and trace case. Here moisture and gases, we are in this example we have set none. Either you can select constant or controlled moist gas source you can set. The next block is a recirculation block by using this feed forward control. In this feed forward control subsystem you can say, design a recirculation block. And the next one is the anode humidifier. In this anode humidifier the proportional control is used here. The next one is the anode gas channel block by using this pipe from the moisture air properties block. And these were anode exhaust block by using this Purge valve. The next one is in the cathode exhaust from the pressure relief valve. Here itself this block also get from MA block, that is a moisture properties Simulink block. This subsystem models a pressure relief valve that maintains a set pressure at port A. This one. So finally, this is a electrical load. This in this example, you can set the electrical load. There's three type of electrical loads. First one is a drive cycle based and ramp and step based. How to select this one? Double click on that electrical load properties. You can set any one of the following scenarios. For first example, I am choosing drive cycle based electrical load and ramp and step block. Later you can discuss this Simulink block also available in my YouTube channel description box. Kindly get this Simulink model for your research and education purpose. Here this one, the important block MEA block, that is a membrane electrode assembly block. It is by using here also by using this source code you can set this block models. What is the electrodes inputs and annotations, parameter checks block, internal parameters, standard cell potential, how to compute molar masses from a specific gas constant, and also specific enthalpy at a standard temperature. Also you can understand by this source code. Okay, here also this block models a stack of membrane electrode assemblies for proton exchange membrane fuel cell, and hydrogen and oxygen are consumed from the connected node and cathode flow channels respectively. Here water vapor is produced at the cathode flow channel. The block also model water transport between anode and cathode. The waste heat dissipated to the thermal mass, connected to this thermal mass. There is a MEA thermal mass block. Here by using this setting menu you can set the parameters, how much cells in the stack, then the cell area you can set membrane thickness and anode gas diffusion layer thickness and cathode gas diffusion layer thickness and exchange current density and what is the maximum current density and charge transfer coefficient and density of dry membrane and equivalent weight of dry membrane also you can set, also by using this reconfigurable or reusable source code available. And this is the important one is the cooling system. By using this cooling system you can see by using the pump control block. In this pump control block we will analyze the control signals like temperature, stack temperature and control signals without delay and with delay. Now you can see the simulation. First one with the coolant subsystem to analyze stack temperature and control output. Now simulation is going on. It takes some more time. Please stay with us. First initially we see the output for coolant subsystems with the stack temperature. This is a stack temperature important one, so that we can analyze the control signals with this feed forward controller to find the stack temperature at the set point versus measured point. These two inputs, one is for set point, another one is for measured temperature, stack temperature. and also control signals with delay and without delay can able to see. Now it's completed. Now we can see the output signal. Here it shows the set point, stack temperature, and in terms of degree per Celsius, and control signal output without delay and with delay. What you discuss in section control signals, stack temperature and control output, it shows. Similarly, you can see the outputs by using this measurement scopes. You can analyze the output. You can see. You can see the current and current voltage and power, and finally the stack temperature. You can see the parallelly by using this Simulink scopes. We can see the output, the stack temperature and control output, the fuel cell current and fuel cell voltage and power and stack temperature. Okay, here the 80 degrees Celsius is constant, you can get. These are output of this fuel cell system Simulink model by using Simscape physical modeling toolbox. Okay, here also you can see the by using this toolbox measurement unit, you can see the peak finder. Here you see the peak finder at the set point value. Here you can see the set point value. Here you can see the value set point, how to measure this one, and this one without delay and with delay control output trace selection. Also by using the measurement unit is signal statistics, you can see, and cursor measurements. Wherever you place the cursor, you can see the time values, the measurement values, you can see. Similarly, for this fuel cell current, voltage and power characteristic, the stack temperature, this is for measurement block, the stack finder, and this is for measurement 2. Then next one is the heat trace selection, and the next one is the electrical. So finally is for measurement 4. This is electrical stack temperature, fuel cell stack temperature. Similarly, you can see by using this tool menu the cursor measurements. Wherever you place the cursor, you can see the measurements unit in terms of degrees. For example, in this measurement we are seeing this stack temperature measurement 4. Whether we are selecting measurement 4 is called as stack temperature. Here, for example, measurement 1, to analyze the current, the cursor is moved. What is the value of this current? Automatically it is the measurement unit, it shows in terms of current. Previously it shows the temperature value, so that in terms of it gives the values in terms of degree Celsius. Here current, here you can see the at which place what is the current it shows by using this trace selection block. Similarly, you can see the peak finder and signal statistic and bi-level measurements. Signal statistic, what is which point has maximum value, minimum value, peak to peak value, and mean value, median, RMS. Also you can see. And then final one is the bi-level measurements. By using bi-level measurement, you can see the transition. What is your I value, what is the edges and rise times. By using this plot, you can understand is the rise time value is 42.921 at this particular point. Okay, what is the sleeve rate, you can see. By using this interactive Simulink scope can analyze all the control signals called current, voltage, power and stack temperature. Okay, now we can up to this we are running this electrical load, drive cycle load. Also, we can choose a ramp and step. Now we can see the reusable source code for plot for fuel cell current voltage curve. The next one, power produced and consumed by the system. Current produced and consumed by the system. So first one is the fuel cell curve, and next one is the efficiency and utilization plot, and temperature in the fuel cell and the fuel coolant system. These points are discussed in the presentation section. The next one is the hydrogen consumed by the fuel cell, and also measure the fuel tank pressure and hydrogen consumed and energy produced. And also these blocks are there. You can see they finally explore the result using Simscape Result Explorer. Here what are the possibilities are there, what are the observations, or what are the designs we are going to discuss. The first one is a figure 1. It shows the fuel cell IV curve, and second one, fuel cell how much power produced and consumed, and the heat dissipated in this heat dissipation unit. And this third figure shows this thermal efficiency and reactive utilization. And this one, the temperature analysis, coolant pump mass flow rate, and the final one is their fuel tank pressure and hydrogen consumed, and this energy produced. There are 5 scopes are available to analyze the fuel cell system. Now, by using interactive Simscape Result Explorer block, can analyze the fuel cell Simulink model by using each and every block, every node. You can understand this concept. Now it is coming, the window is coming. It's called the Simscape Result Explorer window. In this node is a root node. Here in this root node, what are the blocks are, what are the subsystems are involved. For example, anode exhaust, anode gas channels, anode humidifier, cathode exhaust, cathode gas channels, and cathode humidifier, cooling system, electrical load, heat dissipation, hydrogen source, MEA thermal mass, membrane, electrode assembly, and oxygen source and recirculation unit. Now you can see the membrane electrode assembly. Here in this membrane electrode assembly, you can see the how much hydrogen produced, hydrogen consumed, and current, anode, and current temperature, pressure. Also each and every block can see the output in terms with the legends, how much this one hydrogen produced and consumed, and in this manner you can see the how much losses are there by using the ohmic resistance, electrode losses by using this. Here also you can analyze this output. Here also by using this one you can set this interactive plot also. Here you can brush this data, how much you can see this brush this data also available. And this by using this one you can make data tips also. You can get a lot of tools are there. Here itself you can insert X label and Y label. You can also give the legend, what is the line. You can set this you can draw the arrow, draw the line, and the text. Finally you can save the figure of edit plots. Windows edit plots tab is also there. You can zoom in the plot, zoom out the plot, and rotate in terms of 3D and brush links. Also you can set the link. That is after that we can generate code also. Matlab script also you can generate. For example, this is for membrane electrode assembly output for all. Now I can able to generate the code for this output. Okay, now you can see the Matlab automatically the code is generated. Okay, you can see this function in this timer function. You can see the time now. This auto generated Matlab on this 13 November and 7:21. You can see this figure here itself. You can make change for your output. Okay, similarly for all types of anodes you can able to see. Also you can import the data what you measured in this block. You can also import this data into workspace, or you also save workspace or import data in terms of CSV format or Excel format. These are use of the Simscape Result Explorer block in this one. Now I can set this ramp. You can choose this ramp load. What will happen you can see. Again I run this model. Sir, in this way we can analyze this fuel cell system with three different sources. There is electrical load. Previous one shows the drive cycle input. Now we are seeing with ramp load. It takes some more time to give the output. Please stay with us. For your analysis purpose, you can set this hydrogen source and oxygen source block system, and also you can analyze this cooling system with this MEA thermal mass block. We can see the output. This is the previous one. By using this signal scope also you can measure. It takes some more time to get this output. Here these all blocks are available in this Simscape modeling, physical modeling toolbox. Now it is going on simulation settings. Now you can see the output in terms of current. This is a ramp value. You can see the output. Similarly, you can see the fuel cell membrane block. This fuel cell curve. You can see the fuel cell curve and how much plot produced by the system with this ramp load, and efficiency and utilization, and hydrogen consumed by the cell, and temperature plot. You can see this is a temperature plot, and this fuel tank pressure and hydrogen consumed. Similarly, you can see the step input. Now you can see when you click in the step input, the electric load is changed. Now you can see the output. Run this model. This is for step signal, step electrical load. Here you can see what will happen, the plot of fuel cell IV curve and the power produced and consumed by the system, and plot efficiency and utilization, and also plot temperature and hydrogen consumed by the fuel cell. By using this MEA thermal mass block, you can also explore the parameters. Also see the definition script. If you double click on that, you can set the set and parameters. Also it is referenced by the Simscape component. Okay, if you learn more about this example means, you can click here. You can get this example values. Here what is the maximum modeling of this one means, this is a hydrogen source with this anode block, and this one oxygen source with this cathode humidifier gas channels. Okay, now we can see the output for this step. This for electrical and this for heat. Okay, this is our step output. Similarly, you can see the fuel cell IV curve, and this one power produced and consumed, and these are plot efficiency, and these are temperature curve. These are hydrogen consumed by the fuel cell, so that you can easily understand the concept of fuel cell system with this hydrogen generated and consumed with this fuel cell with these different types of scopes. Here also we can see the three different electrical loads. We can analyze the performance of the fuel cell with this example. And also important thing is this MA block code. Using this block code you can set the electrodes, what is the inputs, what is the thermal ports for each generation, and the parameters checks block, and internal parameters values, and internal cell potential, how to compute the molar masses from the specific gas constants. Also you can see this script. And the final one is the MEA model workspace to set the parameters. Is an important block in the simulation example, Simulink example. Here itself we can see the each and every block modeling. Here from what is a from unit, what is the in and out, what is your block data types. It is in column view or block data types. You can set this one. Subsystem code also you can see. Finally we'll set the code generation and system reference. Once you what are the contents of this fuel cell Simulink example, each and every node it shows. Also you can make the block with this block parameter. We can set this subsystem settings also. Also you can convert a subsystem to a reference subsystem with content saved in a separate file also by using this model explorer. Like Simulink result explorer is an interactive analysis explorer for each and every model of this Simulink block. Okay, for example, I am choosing this one. You can set this temperature. In this one, don't go for each and every subsystem. Here itself in this model explorer, you can see. So, for example, PS Simulink converter. What is the output signal unit is in terms of kilowatts? You can see. In heat flow sensor, you can see the source code. For example, it's a heat flow sensor script. Okay, in this way, you can analyze the fuel cell system, how much hydrogen produced and consumed by the fuel cell. Also you can plot and analyze the different types of parameters called power, efficiency, utilization, and temperature. Also the I hope I understand this concept of PEM fuel cell with this Simscape physical modeling. Okay, if you have any queries or any doubts, you mention the comments in my YouTube channel box. We'll try to rectify. Also the Simulink file is available in my YouTube channel description box. Kindly download it for your education purpose. Thanks for watching. Thank you.